Hello there, and welcome to my channel. I'm so glad you're here tonight, wherever in the world you might be listening from. Whether you've had one of those days that felt like it stretched on forever, or your mind is buzzing with 1,000 thoughts that won't settle, or perhaps you simply love drifting off to the gentle rhythm of scientific wonder, this video is made just for you. Tonight, we're going to explore something truly extraordinary. Something that wraps around our entire planet like an invisible embrace, protecting us every moment of every day without us even knowing it's there. We'll be gently wandering through the story of Earth's magnetic field, our planet's most faithful guardian, that shields us from the cosmic storms raging through space. But before we begin this peaceful journey, I'd love to know, where are you listening from tonight? Are you tucked under blankets as the stars appear outside your window? Or perhaps it's morning where you are, and you're starting your day with a bit of cosmic curiosity. What time is it in your corner of the world right now? If you find these sleepy explorations soothing, I'd be ever so grateful if you gave this video a gentle like and perhaps tapped that subscribe button. It helps other sleepy scientists find their way to this calm corner of the universe, and it means I can keep creating these soft journeys through the wonders of science for all of us. Now, I do hope this isn't so fascinating that it accidentally keeps you awake, though if it does, at least you'll drift off knowing a little more about the invisible forces that keep our world safe and sound. Not such a terrible trade, really. So settle in, let your breathing slow, and let's take a quiet stroll through the story of Earth's magnetic field, that silent sentinel that has been standing guard over our little blue planet for billions of years. Imagine, if you will, that you're floating high above Earth in the perfect silence of space. From up there, our planet looks serene, a beautiful marble of swirling blues and whites suspended in the cosmic dark. But what you can't see from that peaceful vantage point is that Earth is actually sitting in the middle of a rather violent neighborhood. The sun, our life-giving star, is not just a gentle source of warmth and light. It's also a massive nuclear furnace that's constantly hurling charged particles out into space at incredible speeds. This stream of particles is called the solar wind, and it's racing toward us right now at over 1,000,000 miles per hour, carrying with it enough energy to strip away atmospheres and turn planets into barren, lifeless rocks. Mars knows this story all too well. Once upon a time, billions of years ago, Mars may have had a thick atmosphere, perhaps even liquid water flowing across its surface. But Mars lost something precious early in its history, something that Earth still has. It lost its magnetic field. Without that invisible shield, the solar wind slowly but relentlessly stripped away Mars's atmosphere, leaving behind the thin, cold world we see today. But Earth? Earth has been different. For over 3 billion years, our planet has been wrapped in an invisible cocoon, a magnetic bubble that gently deflects these cosmic storms away from us. This protective embrace is so effective, so perfectly tuned, that most of us go our entire lives without even thinking about it. Yet right now, as you listen to these words, this magnetic field is hard at work. It's guiding charged particles from the sun around our planet, like water flowing around a smooth stone in a stream. It's preventing our atmosphere from being torn away into space. It's keeping the very air we breathe safe and sound. And perhaps most wonderfully, sometimes this usually invisible guardian makes itself known in the most beautiful way imaginable. When conditions are just right, when the solar wind is particularly strong and the magnetic field lines dance just so, we get to witness one of nature's most breathtaking displays. The aurora borealis in the north, the aurora australis in the south, those shimmering curtains of green and blue and purple light that dance across the polar skies, are actually our magnetic field made visible, a gentle reminder of the constant protection that surrounds us. But what exactly is this magnetic field? How does it work? And why does Earth have one when so many other worlds do not? The story begins deep beneath our feet, deeper than any human has ever travelled, in the very heart of our planet. At Earth's centre lies a core of iron and nickel, heated to temperatures that rival the surface of the sun. This core isn't just sitting there quietly. It's a dynamic, churning system, with liquid metal flowing in vast currents through the outer core, while the inner core, solid due to the immense pressure, slowly rotates. This motion, this constant stirring of molten metal, creates something remarkable. It generates electric currents, and those electric currents create magnetic fields. It's the same principle that powers the generators in a power plant or the dynamo on a bicycle, just on a planetary scale. Earth, in essence, is a massive electromagnet, powered by the heat left over from its formation and the decay of radioactive elements deep within. The magnetic field that emerges from this geological dynamo is both simple and wonderfully complex. At its heart, it's like the field you might have explored in school with iron filings and a bar magnet, with field lines that loop from one pole to the other. But Earth's field is three-dimensional, dynamic, and constantly shifting. The field lines emerge from the southern magnetic pole, curve gracefully through space, and dive back into the northern magnetic pole. But here's something delightfully confusing, if you're still awake enough to appreciate it. Earth's magnetic north pole, the one your compass points to, is actually near the geographic south pole in magnetic terms, and the magnetic south pole is near the geographic north. It's as if the planet decided to keep us on our toes by flipping the usual conventions upside down. These magnetic field lines extend far out into space, creating what scientists call the magnetosphere. It's not quite spherical, despite the name. The solar wind compresses it on the side facing the sun, creating a bow shock like the wake of a boat cutting through water. On the night side of Earth, the magnetosphere stretches out into a long tail that extends far beyond the orbit of the Moon. Within this magnetic bubble, we're remarkably safe. The charged particles of the solar wind, mostly protons and electrons, cannot easily cross magnetic field lines. They're trapped, deflected, or guided along the field lines to the polar regions, where they create those beautiful auroras we mentioned earlier. But our magnetic field is far from perfect or unchanging. It's a living, breathing thing that shifts and fluctuates with time. The magnetic poles wander slowly across the surface, sometimes moving dozens of miles in a single year. The strength of the field varies from place to place and from year to year. And every so often, in a process that still mystifies scientists, the entire field can flip completely, with north becoming south and south becoming north. These magnetic reversals have happened hundreds of times throughout Earth's history, recorded in the iron-rich rocks that cooled and solidified over millions of years. When molten rock cools, tiny magnetic minerals within it align with Earth's magnetic field like countless microscopic compass needles, preserving a record of the field's direction at that moment in time. By studying these ancient magnetic signatures, scientists have discovered that our planet's magnetic field has a rather dramatic personality. Sometimes it's strong and stable for millions of years. Other times it weakens dramatically, fluctuates wildly, or even disappears entirely for brief periods during the reversal process. And here's something that might give you pause as you settle in for sleep. Right now, in our current geological moment, Earth's magnetic field is weakening. It's been declining in strength for the past 150 years, losing about 15% of its intensity. The magnetic North Pole is racing across the Arctic faster than it has in centuries, moving from northern Canada towards Siberia at a pace that keeps geophysicists scrambling to update navigation systems. Does this mean we're heading toward a magnetic reversal? Possibly. The last one occurred about 780,000 years ago, which means we're somewhat overdue by historical standards. But before you worry too much, remember that life on Earth has survived hundreds of these reversals. They're dramatic from a geological perspective, but they typically take thousands of years to complete, giving life plenty of time to adapt. During a reversal, the magnetic field doesn't simply switch off and then back on in the opposite direction. Instead, it becomes more complex, sometimes developing multiple poles, or creating a patchwork of magnetic regions pointing in different directions. The overall field weakens significantly, but it doesn't disappear entirely. Still, even a weakened magnetic field would mean increased exposure to cosmic radiation and solar storms. We might see auroras at lower latitudes, more disruption to satellites and power grids, and perhaps a slight increase in radiation exposure for people flying at high altitudes. But life itself would continue, just as it has through countless reversals before. What's truly remarkable is that scientists are only now beginning to understand just how crucial our magnetic field has been to the development of life on Earth. Without it, our planet might have followed the same path as Mars, slowly losing its atmosphere to the relentless solar wind. The water that fills our oceans, the air that we breathe, the delicate balance of gases that makes complex life possible, all of it exists partly because we've been wrapped in this protective magnetic embrace for billions of years. The magnetic field also plays subtle roles in the behavior of many living creatures. Birds, sea turtles, and many other animals use Earth's magnetic field for navigation, following invisible highways across continents and oceans with a precision that still amazes researchers. Some scientists even suspect that humans might have a vestigial magnetic sense, though it's far weaker than in other animals. As we continue our gentle exploration, we'll discover how scientists first realized that our planet was magnetic, how they mapped the invisible field lines that surround us, and what modern research is revealing about the complex dance between Earth's molten core and the cosmic forces that surround us. We'll learn about the spacecraft that venture into the magnetosphere to study this invisible shield firsthand, and we'll explore what the future might hold for our planet's magnetic protection. We'll discover how the northern lights are born in the collision between solar particles and our magnetic field, and why different planets in our solar system have such different magnetic personalities. But for now, as we pause in our journey through this invisible realm, take a moment to appreciate the quiet marvel that surrounds you. Right now, at this very moment, Earth's magnetic field is gently guiding charged particles away from our atmosphere, maintaining the delicate conditions that allow you to breathe, to think, to dream. It's a reminder that we live in a universe filled with invisible forces, silent guardians, and protective embraces that work tirelessly to keep our little world safe and habitable. The magnetic field asks for nothing in return. It simply exists, a gift from the churning heart of our planet, a shield forged in the furnace of Earth's core and extended into space, like invisible arms holding us close. So as you settle deeper into comfort, remember that you're not just resting in your bed or your chair. You're resting within a vast magnetic cocoon that has been sheltering Earth for eons, a cosmic embrace that connects the spinning iron in our planet's heart to the dancing lights in the polar skies. Tonight, let's take a peaceful journey back through time, back to when humanity first began to suspect that our planet might be more than just a ball of rock spinning through space. Because the story of how we discovered Earth's magnetic field is filled with curious minds, patient observations, and those wonderful moments when the invisible suddenly becomes beautifully clear. Picture, if you will, ancient Chinese navigators over 2,000 years ago, floating quietly down rivers in wooden boats. They had discovered something peculiar about certain stones, lodestones they called them, pieces of naturally magnetized iron ore that had a strange habit. When suspended on a string or floated on water, these stones would always point in the same direction, as if drawn by some invisible hand toward the north. These early compass makers didn't understand why this happened, but they recognized its usefulness. Here was a way to navigate even when the stars were hidden by clouds, even when the sun was nowhere to be seen. The lodestone knew something about directions that seemed to transcend the visible world. For centuries, this magnetic behavior remained a mystery wrapped in folklore and superstition. Some believed the stones were drawn toward magnetic mountains hidden somewhere in the far north. Others thought they were attracted to the North Star itself, as if the heavens were pulling them upward through some celestial magnetism. It wasn't until the late 16th century that a remarkable English physician named William Gilbert began to piece together the truth. Gilbert was fascinated by magnetism, and he conducted careful experiments with lodestones and iron needles in the quiet of his study. But his most brilliant insight came when he carved a sphere from a piece of lodestone and mapped the behavior of small compass needles all around its surface. What he discovered was revolutionary. The needles didn't just point in random directions, they formed a pattern, a beautiful, orderly arrangement of lines that curved from one pole of the sphere to the other. And here's the moment that must have sent chills down his spine. The compass needles around his magnetic sphere behaved exactly like compass needles around the Earth. In 1600, Gilbert published his findings in a book with a wonderfully grand title, De Magnete, Magnetisque Corporibus, et de Magno Magneti Tellure, which roughly translates to On the Magnet and Magnetic Bodies, and on that great magnet the Earth. Gilbert had realized something extraordinary. Earth itself was a giant magnet. This was a profound shift in thinking. For the first time, humans began to understand that our planet possessed invisible properties, forces that extended beyond its surface into the space around it. The compass needle wasn't being pulled towards some distant mountain or star. It was responding to the magnetic field of the very ground beneath our feet. But Gilbert's work was just the beginning. Over the following centuries, explorers and scientists began to map this invisible field with increasing precision. They discovered that magnetic north wasn't quite the same as geographic north, that compass readings varied depending on where you stood on the planet's surface, and that the magnetic field itself seemed to change slowly over time. One of the most dedicated of these magnetic explorers was Alexander von Humboldt, a German naturalist who travelled the world in the early 1800s, measuring magnetic readings from South America to Siberia. Humboldt was the first to notice that magnetic storms, sudden disturbances in compass readings, seemed to happen simultaneously across vast distances. This suggested that something was affecting Earth's magnetic field on a global scale. What Humboldt couldn't have known is that these magnetic storms were our first clue about the solar wind and space weather. When charged particles from the Sun interact with Earth's magnetic field, they can cause temporary disruptions that ripple around the globe. The compass needles in his era were already whispering secrets about cosmic forces that wouldn't be fully understood for another century and a half. As the 19th century progressed, the mapping of Earth's magnetic field became an international endeavour. Observatories were established around the world, all taking synchronized measurements of magnetic declination and inclination. Scientists began to realize that the magnetic field wasn't uniform, it had regions of strength and weakness, areas where the field lines dove steeply into the Earth, and others where they ran nearly horizontal. They discovered the magnetic equator, an invisible line around the globe, where compass needles point horizontally rather than dipping toward the ground. They found magnetic anomalies, places where local geological features created their own magnetic signatures that could deflect compass readings by significant amounts. But perhaps most intriguingly, they began to notice that the magnetic field was wandering. The magnetic poles weren't fixed points, they drifted slowly across the landscape from year to year. Maps that were accurate in one decade needed updating in the next. Earth's magnetic field was alive, dynamic, constantly in motion. This realization led to one of the great mysteries of 19th century science. If Earth was indeed a giant magnet, what was making it magnetic? The planet couldn't be made of lodestone. Iron ore wasn't nearly abundant enough. And even if it were, scientists knew that heating iron above a certain temperature destroyed its magnetic properties. Since Earth's interior was almost certainly hot, this seemed to rule out permanent magnetism as an explanation. The puzzle deepened when geologists began to study the magnetic properties of rocks. They found that volcanic rocks, when they cooled, preserved a record of Earth's magnetic field at the moment of their formation. And these ancient magnetic signatures told a startling story. Throughout history, Earth's magnetic field had not only wandered and fluctuated, It had completely reversed direction hundreds of times. Rocks that formed millions of years ago sometimes pointed south when they should have pointed north, as if at those ancient moments, Earth's magnetic poles had been flipped upside down. This was the first evidence of magnetic reversals, though scientists wouldn't fully understand their significance until the mid-20th century. The breakthrough came when researchers began to understand Earth's internal structure. Through the study of seismic waves from earthquakes, they mapped the planet's interior and discovered the liquid iron outer core. Here, finally, was a mechanism that could explain Earth's magnetism. The flowing, churning motion of liquid iron could generate electric currents, and those currents could produce magnetic fields. This process, called the geodynamo, finally solved the mystery that had puzzled scientists for centuries. Earth wasn't a permanent magnet. It was an electromagnet, powered by the constant motion in its molten core. The magnetic field lines that Gilbert had mapped, the wandering poles that 19th century explorers had documented, the reversals recorded in ancient rocks, all of it made sense in the context of a dynamic, fluid system deep within our planet. But understanding the source of Earth's magnetism was only the beginning. In the 1952nd, as rockets began to carry instruments beyond the atmosphere, scientists made another remarkable discovery. Earth's magnetic field didn't just extend to the surface, it reached far out into space, creating a vast bubble of magnetic influence around our planet. This was the discovery of the magnetosphere, that invisible shield we discussed earlier. Suddenly, Earth's magnetic field wasn't just a curiosity for navigators and geologists, it was revealed as a crucial protective barrier standing between our planet and the harsh environment of space. The space age brought instruments that could measure the magnetic field directly, map its three-dimensional structure, and monitor its constant fluctuations. Satellites revealed the bow shock, where the solar wind first encounters our magnetic field, the radiation belts where charged particles become trapped, and the long magnetic tail that streams away from Earth on the night side. These discoveries transformed our understanding of what it means to live on a magnetic planet. We learned that the aurora, those beautiful lights that had inspired wonder and folklore for millennia, were actually the visible signature of our planet's magnetic shield at work. When charged particles from the solar wind managed to penetrate the magnetosphere, they followed magnetic field lines down toward the polar regions, colliding with atmospheric gases and lighting up the sky in brilliant displays of green, blue, and red. We discovered that our magnetic field is in constant communication with the sun, responding to changes in solar activity with storms and fluctuations of its own. During periods of high solar activity, when the sun hurls particularly intense bursts of charged particles our way, our magnetic field can become so disturbed that it affects technology on Earth. Power grids can be disrupted, satellites can malfunction, and radio communications can be interfered with. Yet through all of these discoveries, perhaps the most profound realization has been how perfectly tuned Earth's magnetic system appears to be for supporting life. The field is strong enough to deflect most harmful radiation, but not so strong that it prevents the formation of the aurora or the occasional penetration of particles that may have played a role in atmospheric chemistry and evolution. The magnetic poles wander just enough to ensure that the field lines don't become too rigid, allowing for the complex interactions with the solar wind that create the magnetosphere's dynamic structure. The reversals that initially seemed chaotic and destructive now appear to be part of a natural cycle that refreshes and reorganizes the field over geological timescales. Modern research continues to reveal new layers of complexity and beauty in Earth's magnetic system. Scientists have discovered that the magnetic field influences cloud formation, affects the behavior of cosmic rays, and may even play a role in climate patterns over very long timescales. They've found that the interaction between our magnetic field and the solar wind creates waves and oscillations that ring through the magnetosphere like music, too low for human ears to hear, but detectable by sensitive instruments. We've learned that other planets tell different magnetic stories. Jupiter has a magnetic field so powerful it could engulf the Sun, generated by metallic hydrogen deep within its massive interior. Saturn's magnetic field is mysteriously aligned almost perfectly with its rotation axis, unlike Earth's tilted field. Venus, similar to Earth in size, has almost no magnetic field at all, leaving its thick atmosphere exposed to the solar wind. These planetary comparisons have helped scientists understand how fortunate Earth has been. Our planet's magnetic field exists because of a delicate balance of factors: the right size for maintaining a molten core, the right rotation rate to drive the dynamo, the right composition to conduct electricity, and perhaps most importantly, the right timing to maintain this system for billions of years. As you rest tonight, surrounded by this invisible magnetic embrace, you're part of a story that spans from ancient Chinese navigators to modern spacecraft, from the molten iron churning thousands of miles beneath your feet to the aurora dancing in polar skies. You're living within a magnetic field that has been Earth's faithful guardian for eons, a protective presence so constant and reliable that most of us never even notice it's there. The magnetic field asks nothing of us, expects nothing in return. It simply exists, a quiet testament to the beautiful complexity hidden within our seemingly simple planet. It reminds us that the universe is full of invisible wonders, forces and fields and influences that shape our world in ways both subtle and profound. So as your breathing slows and your thoughts begin to drift, remember that you're not just resting in the safety of your home, but within the gentle embrace of Earth's magnetic field. That ancient shield that has been standing guard over our little blue world since long before the first humans looked up at the stars and wondered what lay beyond. Tonight, let's take a moment to wonder about something truly remarkable. Right now, as you listen to these words, there are invisible rivers of molten iron flowing thousands of miles beneath your feet, moving in patterns so complex and beautiful that they would make the most intricate dance seem simple by comparison. These flowing currents of liquid metal are writing the story of our planet's magnetic field in real time, creating the very shield that keeps us safe. The journey to the center of Earth is one we can only take in our imagination, but it's a journey worth making. Picture yourself descending through layers of rock and metal, past the deepest ocean trenches, beyond the reach of any drill or probe. The temperature rises as you go deeper, the pressure mounting until it would crush any earthly material to dust. Yet somehow in this inferno at the heart of our world, the most delicate and essential process is taking place. At about 1,800 miles down, you would encounter something extraordinary. The solid rock gives way to liquid iron, heated to temperatures that would vaporize most substances instantly. This is Earth's outer core, a sphere of molten metal larger than the planet Mars, spinning and churning in the darkness like a vast underground ocean of liquid lightning. But this isn't just any liquid. This iron is so hot, so energetic, that it conducts electricity like the copper wires in your walls, only infinitely more powerfully. As it flows in great currents driven by the planet's rotation and the slow cooling of Earth's interior, it carries electric currents with it, and wherever electric currents flow, magnetic fields are born. The physics here are the same as in any generator or dynamo, but the scale is almost incomprehensible. We're talking about currents of liquid metal flowing through a space larger than a planet, generating magnetic fields powerful enough to reach beyond the moon. It's as if Earth has a massive electrical generator at its heart, powered not by coal or water or wind, but by the primordial heat left over from the planet's violent birth 4.5 billion years ago. The patterns these currents create are endlessly fascinating. Computer simulations of the geodynamo reveal swirling vortices and spiraling flows that look almost like abstract art, or perhaps like the weather patterns of some impossible metallic atmosphere. The iron flows in columns and sheets, rises and falls in convection cells, and occasionally breaks into turbulent eddies that can persist for decades or centuries. These flowing patterns are why Earth's magnetic field is so wonderfully complex and unpredictable. Unlike the neat, orderly field of a bar magnet, our planet's magnetism is alive, constantly shifting and evolving as the currents in the outer core reorganize themselves. Sometimes the flow strengthens the main magnetic field. Sometimes it creates secondary fields that compete with the primary one. And sometimes, in ways that still puzzle scientists, these competing fields can grow strong enough to overcome the main field entirely, triggering one of those dramatic magnetic reversals we mentioned earlier. The most recent of these reversals has a rather ominous name, the Carrington Event, and it occurred about 42,000 years ago. During this period, which lasted for several centuries, Earth's magnetic field weakened dramatically, and the poles wandered across the globe before eventually settling into their reversed positions. The field was so weak during this time that cosmic radiation reaching Earth's surface increased significantly. Some researchers have suggested that this magnetic chaos might have contributed to the extinction of Neanderthals and the mysterious disappearance of Australia's giant marsupials around the same time. Cave paintings from this period show unusual red ochre handprints, possibly indicating that early humans were spending more time underground to escape increased radiation. Even the aurora would have appeared at latitudes where they'd never been seen before, painting the skies with strange lights that must have seemed both beautiful and terrifying. But life, as it always does, adapted and survived. The magnetic field eventually strengthened again, the poles settled into their new configuration, and the world continued spinning through space under its restored, invisible shield. This resilience is one of the most comforting aspects of Earth's magnetic system, its ability to rebuild itself even after apparent collapse. Today's magnetic field is far from uniform. If you could somehow see it, stretching out into space around our planet, it would look rather like a cosmic teardrop. On the side facing the sun, the solar wind compresses our magnetosphere into a bullet-like shape, with a sharp bow shock about 40,000 miles from Earth, where the solar wind first encounters our magnetic barrier. On the night side, away from the solar wind's pressure, our magnetic field streams out into a long tail that extends well beyond the orbit of the Moon. This magnetotail, as scientists call it, is a dynamic region where magnetic field lines stretch and snap like cosmic rubber bands, occasionally releasing bursts of energy that send charged particles racing back toward Earth to create those spectacular auroral displays. Within this magnetic cocoon lie the Van Allen radiation belts, named after the American physicist James Van Allen, who discovered them in 1958 using data from the first American satellites. These belts are regions where our magnetic field traps charged particles from the solar wind, holding them in stable orbits around Earth, like invisible donuts of radiation. They serve as a kind of magnetic prison for dangerous particles that might otherwise reach our atmosphere. The Van Allen belts were one of the first major discoveries of the space age, and they immediately posed a challenge for human space exploration. Astronauts traveling to the Moon had to pass through these radiation belts quickly to avoid dangerous exposure. Even today, satellites must be carefully shielded to survive in these regions, and spacecraft electronics can be damaged by the intense radiation environment. But these same radiation belts that pose challenges for space travelers are actually part of our planet's defense system. By trapping dangerous particles far from Earth's surface, they prevent much of this radiation from reaching our atmosphere. It's another example of how Earth's magnetic field doesn't just deflect threats, it actively manages them, turning potentially harmful cosmic particles into a protective barrier. The study of Earth's magnetosphere has revealed phenomena that sound like they belong in science fiction but are perfectly real. There are magnetic reconnection events, where field lines snap and recombine explosively, releasing energy equivalent to millions of atomic bombs. There are plasma waves rippling through the magnetosphere at frequencies that, if converted to sound, would create an eerie cosmic symphony. Scientists have discovered magnetic flux ropes, twisted bundles of magnetic field lines that can stretch for thousands of miles through space. They found magnetic islands, isolated pockets of reversed magnetic field that drift through the magnetotail like cosmic icebergs. And they've observed chorus waves, electromagnetic oscillations that sweep up and down in frequency like the calls of invisible space whales. All of this complexity, all of this cosmic drama playing out in the invisible realm around our planet, stems from that churning sea of molten iron thousands of miles beneath your feet. The geodynamo that powers Earth's magnetic field is one of the most sophisticated and long-running machines in the solar system, operating continuously for billions of years, without maintenance, without fuel, without any input, except the gradual cooling of our planet's interior. Yet for all our scientific understanding, the geodynamo still holds mysteries. Scientists can't predict exactly when the next magnetic reversal will occur, or how long it will last, or what the field strength will be afterward. They can't fully explain why Earth's magnetic field has the particular strength and configuration it does, or why it sometimes weakens in certain regions while strengthening in others. One of the most intriguing current mysteries is something called the South Atlantic Anomaly, a region stretching from South America to southern Africa, where Earth's magnetic field is significantly weaker than elsewhere. In this area, the Van Allen radiation belts dip closer to Earth's surface, creating increased radiation exposure for satellites and astronauts passing through. Some scientists wonder if this anomaly might be an early sign of an impending magnetic reversal, a crack in our magnetic armor that could eventually split our field into multiple competing poles. But even as scientists work to understand these mysteries, we can take comfort in the remarkable stability of Earth's magnetic system over the timescales that matter for human civilization. While the field may wander and fluctuate over centuries and millennia, on the scale of human lifetimes it provides remarkably consistent protection. The magnetic field that guided the first compass needles in ancient China is essentially the same field that guides GPS satellites today. The aurora that inspired Norse mythology still dance in the same polar skies where modern photographers travel to capture their beauty. The magnetic north that drew early Arctic explorers continues to beckon to adventurers and scientists seeking to understand our planet's invisible architecture. This continuity across human history is part of what makes Earth's magnetic field so remarkable. It's been our faithful, invisible companion throughout the entire journey of human civilization. It protected the first humans as they migrated across continents, it guided the ships of early explorers as they mapped unknown oceans, and it continues to shield the International Space Station as it orbits overhead tonight. The magnetic field connects us not just to our planet's molten heart, but to the broader cosmos. When we see an aurora, we're witnessing the interaction between Earth's magnetic field and particles that began their journey at the sun. When we use a compass, we're tapping into a force that extends from our planet's core out into the vacuum of space. When we worry about solar storms disrupting our technology, we're acknowledging our dependence on the delicate balance between cosmic forces and terrestrial magnetism. In recent years, scientists have begun to appreciate just how rare and precious a strong magnetic field might be. As we discover more planets orbiting other stars, we're learning that magnetic fields like Earth's may be relatively uncommon. Many rocky planets might lack the right conditions to generate and maintain strong magnetic fields over billions of years. This rarity makes Earth's magnetic field seem even more special, even more worth protecting and understanding. It's not just a convenient feature of our planet, it may be one of the key ingredients that made complex life possible here. Without it, Earth might have lost its atmosphere early in its history, leaving behind a barren world like Mars instead of the vibrant, living planet we call home. As you drift towards sleep tonight, surrounded by this invisible magnetic embrace, perhaps you can sense the quiet miracle that surrounds you. Every breath you take, every dream you'll dream, every morning you'll wake to see the sun rise, All of it is possible partly because of the molten currents flowing in Earth's heart, generating the magnetic field that has stood guard over our world for eons. The magnetic field asks for nothing, expects nothing, demands nothing. It simply exists, a gift from the physics of our planet, a protective presence so constant and reliable that we barely notice it's there. Yet it connects us to forces and phenomena that span from the center of the Earth to the edge of space, from the birth of our planet to the dancing lights in tonight's polar skies. So rest peacefully, knowing that you're held not just by gravity's pull, but by magnetism's gentle shield, a force both ancient and eternal, that will continue its faithful watch long after we've all returned to the stardust from which we came. Sometimes, in the quiet hours of the night, the most extraordinary things happen without us even knowing. While you've been resting, while cities sleep and the world turns dark, something magical has been taking place high above your head. The aurora, those ethereal curtains of light that dance across polar skies, have been putting on their silent show, painting the darkness with colours that seem almost too beautiful to be real. These northern and southern lights, the aurora borealis and aurora australis, are perhaps the most enchanting way our planet's magnetic field reveals itself to us. They're like love letters written in light, messages from the sun delivered through the postal system of Earth's magnetosphere. And tonight, as we settle deeper into our exploration of these invisible forces, let's take a gentle journey to understand how these cosmic conversations create some of the most breathtaking displays in all of nature. Picture, if you will, a charged particle that began its journey at the sun. This tiny traveller, perhaps a proton or an electron, was hurled into space during one of the sun's frequent tantrums, a solar flare or coronal mass ejection, that sent billions of particles racing through the void at speeds that would make a jet plane seem like it's standing still. For days, this particle has been crossing the emptiness between worlds, part of the solar wind that constantly streams away from our star. It survived the cold of space, the vacuum that would instantly destroy any earthly traveller. And now, finally, it approaches Earth, moving at over 1 million miles per hour toward our little blue world. But Earth is ready. Our magnetic field extends far out into space, creating that protective bubble we call the magnetosphere. When our tiny solar traveller encounters this invisible barrier, something wonderful begins to happen. The magnetic field doesn't destroy the particle or simply bounce it away. Instead, it begins a complex dance, a cosmic choreography that will eventually paint the sky with light. Most particles are deflected around Earth, flowing past us like water around a stone in a stream. But some, the lucky few, find their way into the magnetosphere through small gaps and weak points in our magnetic shield. These particles become trapped in our planet's magnetic field lines, following invisible highways that curve and spiral through space. The journey these particles take is extraordinary. They might spend hours or even days bouncing back and forth along magnetic field lines, accelerated to incredible speeds by the very forces that captured them. They travel from one side of Earth to the other, following magnetic pathways that loop far out into space before diving back toward our planet. And it's when these particles finally approach Earth that the real magic begins. As they follow the magnetic field lines down toward the polar regions, they encounter something they haven't seen since leaving the sun, an atmosphere. Earth's thin envelope of gases, mostly nitrogen and oxygen, extends upward for hundreds of miles above the surface. When a charged particle moving at tremendous speed collides with a gas molecule in our atmosphere, something beautiful happens. The collision transfers energy to the gas molecule, exciting its electrons and lifting them to higher energy levels. But these excited states can't last. Within fractions of a second, the electrons fall back to their normal energy levels, releasing the extra energy as light. The color of that light depends on which type of gas molecule was struck and at what altitude the collision occurred. Oxygen, when hit at high altitudes around 200 miles up, glows with an ethereal red light, lower down, at altitudes of 60 to 100 miles, oxygen produces the familiar green glow that dominates most auroral displays. Nitrogen adds its own contribution, creating blue and purple hues that weave through the green curtains like cosmic embroidery. But aurora aren't just random flashes of light. They follow the invisible architecture of Earth's magnetic field, creating curtains and arcs and spirals that mirror the field lines themselves. When you see an aurora dancing across the sky, you're actually seeing the shape of our planet's magnetic field made visible, the invisible highways that charged particles travel painted in light across the darkness. The patterns are endlessly fascinating. Sometimes the aurora appears as a gentle arc stretching across the horizon, a soft green glow that might be mistaken for the lights of a distant city. Other times it erupts into towering rays that seem to reach toward the stars, pillars of light that pulse and flicker with their own mysterious rhythm. During particularly active periods, when the sun has sent an especially strong burst of particles our way, the aurora can fill the entire sky with dancing curtains of light. These displays can be so bright they cast shadows on the snow below, so active that they seem to writhe and twist like living things. Colours that are usually rare, deep purples and brilliant reds, paint the sky in hues that photographers struggle to capture and poets struggle to describe. What makes these displays even more remarkable is their connection to events happening 93 million miles away. When astronomers observe a solar flare erupting from the sun's surface, they can often predict that Earth will see enhanced auroral activity a few days later. When those charged particles complete their journey across the solar system, it's as if the sun is sending us messages of light, cosmic postcards that take days to deliver and arrive painted across our polar skies. The indigenous peoples of the Arctic have known and celebrated the aurora for thousands of years, long before science could explain their origin. To the Inuit, the lights were the spirits of the dead playing in the sky. Norse mythology described them as the bridge that carried fallen warriors to Valhalla. Finnish folklore spoke of the firefox, a magical creature whose tail swept across the snow and threw sparks into the sky as it ran. These ancient stories capture something that scientific explanation sometimes misses: the sense of wonder and mystery that the aurora inspire. Even when we understand the physics of charged particles and magnetic field lines, even when we can predict auroral activity with satellites and computer models, the lights retain their power to inspire awe. Modern aurora watchers travel thousands of miles to witness these displays, bundling up in Arctic gear to stand in the cold darkness of polar nights. They know that aurora are most common during the equinoxes, when Earth's tilted magnetic field aligns just right with the solar wind. They understand that clear, dark skies far from city lights offer the best viewing. Yet when the lights begin to dance, when the sky erupts in green and purple and red, all that knowledge fades into the background, replaced by something more primal, a sense of connection to forces far greater than ourselves. Photography has allowed us to share these displays with people who may never travel to polar regions, but cameras capture only part of the story. They can freeze the colors and shapes of aurora, but they can't capture the movement, the way the lights seem to breathe and pulse with their own life. They can't record the absolute silence that often accompanies these displays, the way the aurora can fill the sky with light while making no sound at all. That silence is part of what makes aurora so magical. Unlike lightning, which announces itself with thunder, or fireworks, which explode with noise and smoke, aurora are purely visual. They're light without sound, motion without substance, beauty without any earthly explanation, until you understand the invisible dance between solar wind and magnetic field. But aurora aren't just beautiful, they're also messengers. Scientists study auroral displays to understand space weather, the conditions in the magnetosphere that affect satellites, power grids, and communication systems. When aurora appear at unusually low latitudes, visible from places like Scotland or northern United States where they're normally never seen, It often indicates a severe geomagnetic storm that could disrupt technology. The same solar storms that create spectacular aurora can also knock out power grids, interfere with GPS signals, and damage satellites. In 1989, a particularly powerful geomagnetic storm caused by a solar flare knocked out the power grid in Quebec, leaving millions without electricity for hours. The aurora from that storm were visible as far south as the Caribbean, painting tropical skies with lights that had never been seen there in recorded history. Yet for every technological challenge they create, aurora also remind us of our connection to the cosmos. They're visible proof that we live on a planet in space, subject to the whims of solar weather, and protected by invisible magnetic forces. They connect us to the ancient past, when our ancestors looked up at the same lights dancing in the same skies, and to the distant future, when aurora will continue to paint polar nights long after our current civilizations have passed into history. The study of aurora has also taught us about other worlds. Jupiter's massive magnetic field creates aurora far more powerful than Earth's, painting its polar regions with lights that would dwarf any earthly display. Saturn, Uranus, and even some of Jupiter's moons have their own auroral phenomena, each one shaped by the unique magnetic environment of its world. These alien aurora help us understand how special Earth's displays really are. Our planet's magnetic field creates aurora that are visible to the naked eye, beautiful enough to inspire art and poetry, but not so intense that they pose a threat to life on the surface. It's another example of the delicate balance that makes our world so perfectly suited for the life that calls it home. As we continue our gentle exploration, we'll discover more about how scientists study our magnetic field, how they predict its behavior, and what they've learned about its history. We'll explore the spacecraft that venture into the magnetosphere to measure magnetic forces directly, and we'll learn about the computer models that help us understand the complex interactions between solar wind and planetary magnetism. We'll also discover how Earth's magnetic field affects not just the grand displays of aurora, but the everyday lives of creatures both great and small. From sea turtles navigating across oceans to birds flying thousands of miles during migration, life on Earth has learned to use our planet's magnetic field as a guide, a compass, and sometimes even as a calendar. But for now, as we pause in our journey through this invisible realm, take a moment to imagine the aurora that may be dancing at this very moment in polar skies. Even if you can't see them from where you are, even if clouds or daylight hide them from view, somewhere on Earth tonight the magnetic field is painting the darkness with light, creating displays of beauty that connect our little world to the vast, energetic cosmos that surrounds us. The aurora ask nothing of us, expect nothing in return. They simply dance when conditions are right, painting temporary masterpieces across the sky that last for minutes or hours before fading back into darkness. They're gifts from the interaction between solar wind and magnetic field, reminders that we live in a universe full of invisible forces and unexpected beauty. So as you settle deeper into rest, perhaps you can imagine those curtains of light swaying in distant polar skies, those cosmic messengers delivering their silent news from the sun. Remember that the same magnetic field creating those beautiful displays is also surrounding you right now, an invisible embrace that extends from Earth's molten heart to the aurora dancing overhead. Tonight, the lights are dancing somewhere, and we are all connected to their gentle glow by the invisible threads of magnetism that bind our world together. Rest well, knowing that above the everyday concerns of earthly life, the cosmos continues its ancient conversation in languages of light and magnetism, beauty and protection, wonder and peace. Tonight, let's embark on a gentle journey into one of the most fascinating aspects of our magnetic story, the incredible ways that life on Earth has learned to sense, use, and navigate by the invisible field that surrounds us. It's a tale of biological compasses, living magnetometers, and creatures that can feel the pull of forces we can barely detect with our most sensitive instruments. Imagine, if you will, a sea turtle hatchling no bigger than your palm, emerging from its sandy nest on a moonlit beach. This tiny creature, having never seen the ocean before, somehow knows exactly which direction to crawl. Not toward the brightest lights, not toward the loudest sounds, but toward the vast expanse of water that will become its home for the next several decades. What guides this remarkable navigation isn't just instinct in the way we usually think of it. Hidden within that small turtle's body are microscopic crystals of magnetite, the same iron-rich mineral that forms natural lodestones. These biological compass needles are so tiny they're measured in nanometers, yet they're perfectly positioned to detect the subtle variations in Earth's magnetic field. As our young turtle makes its way to the water and begins its epic journey across ocean basins, it's reading a magnetic map that we're only beginning to understand. The turtle can sense not just the direction of magnetic north, but also the angle at which magnetic field lines intersect the Earth's surface, what scientists call magnetic inclination. This gives the turtle a sense of latitude, helping it navigate along invisible highways that crisscross the ocean. But it gets even more remarkable. As the turtle grows and matures, it memorizes the magnetic signature of its birth beach, a unique combination of magnetic intensity and inclination that serves as a kind of magnetic fingerprint. Decades later, when it's time to return and lay eggs of its own, the turtle can use this magnetic memory to find its way back to the very stretch of coastline where its own life began. Sea turtles aren't alone in this magnetic mastery. Thousands of miles above the ocean, birds are using Earth's magnetic field to perform navigation feats that would challenge our most sophisticated GPS systems. Arctic terns, those remarkable seabirds that migrate from Arctic to Antarctic and back again each year, somehow manage to find their way across 44,000 miles of open ocean and empty sky. Tucked away in the beaks of these birds are clusters of iron-rich cells that function as biological magnetometers. But unlike a simple compass that just points north, these avian magnetic sensors can detect incredibly subtle variations in the magnetic field's strength and direction. A bird flying from Alaska to Argentina can sense when it's drifted off course by detecting tiny changes in the magnetic landscape below. Even more fascinating is the discovery that some birds may actually see magnetic fields. Special proteins in their eyes, called cryptochromes, appear to be sensitive to the quantum effects that occur when magnetic fields interact with certain chemical reactions. This means that as a migrating bird looks down at the landscape below, it might see not just forests and rivers and mountains, but also glowing patterns of magnetic field lines overlaid across its visual field, like a cosmic roadmap. The evidence for this magnetic vision is still being studied, but laboratory experiments have shown that disrupting these quantum processes with radio waves can disorient migrating birds. It suggests that what we experience as an invisible force might appear to some creatures as patterns of light and shadow, a hidden layer of reality that guides their epic journeys across continents. Closer to the ground, honeybees use magnetic sensitivity for more local navigation. These industrious insects can detect changes in Earth's magnetic field caused by underground mineral deposits, power lines, and even large metal objects. When a bee discovers a rich patch of flowers miles from the hive, it uses a combination of visual landmarks, polarized light patterns, and magnetic cues to remember the location and communicate it to other bees through their famous waggle dance. But perhaps most intriguingly, bees appear to be sensitive to the daily variations in Earth's magnetic field caused by our planet's rotation and its interaction with the solar wind. Some researchers believe bees might use these subtle magnetic rhythms as a kind of clock, helping them coordinate their activities with the natural cycles of day and night. Even smaller creatures show remarkable magnetic abilities. Certain bacteria contain chains of magnetite crystals that act like tiny compass needles, helping them navigate toward the muddy sediments at the bottom of ponds and lakes where they find the oxygen-poor conditions they prefer. These magnetotactic bacteria, as they're called, were among the first living things discovered to use Earth's magnetic field for navigation. Under a microscope, You can actually watch these bacteria align themselves with magnetic field lines and swim in formation like microscopic military units. They're so sensitive to magnetism that researchers use them to detect magnetic anomalies in rock samples, employing living creatures as biological instruments to study Earth's geological history. The magnetic sense isn't limited to creatures that travel great distances. Mole rats living in underground tunnel systems use magnetic cues to maintain their sense of direction in the dark, ensuring they can find their way back to food stores and nesting areas. Foxes hunting for mice beneath snow appear to use magnetic field lines to judge the perfect angle for their pouncing attacks, aligning their leaps with magnetic north for maximum success. Even domestic animals retain some magnetic sensitivity. Cows and sheep tend to align their bodies with magnetic field lines when grazing, though they seem to ignore this magnetic preference when strong winds or other factors interfere. Dogs, when relieving themselves, often choose to align their bodies along the north-south magnetic axis, though most pet owners have probably never noticed this peculiar preference. But what about humans? Do we retain any remnant of the magnetic sense that guides so many other creatures? The answer is complicated and still being researched, but there are tantalizing hints that we might possess a vestigial magnetic sense, buried deep in our evolutionary past, but not entirely lost. Some studies have suggested that people can unconsciously orient themselves using magnetic cues when other navigation aids are removed. Subjects wearing blindfolds in unfamiliar locations sometimes show a slight but statistically significant tendency to point toward magnetic north when asked to indicate directions. The effect is weak and inconsistent, nothing like the precision of migrating birds or sea turtles, but it suggests that some magnetic sensitivity might persist in our species. There are also anecdotal reports from people who live in areas with strong magnetic anomalies. Some residents near large iron ore deposits claim they can sense changes in the local magnetic field, reporting headaches or disorientation when the magnetic environment shifts. While these reports are difficult to verify scientifically, they hint at the possibility that humans might be more magnetically aware than we typically realize. More concrete is the discovery that human cells contain small amounts of magnetite, the same iron oxide mineral that forms biological compasses in other animals. These magnetic crystals are found in various tissues, including the brain, though their function in humans remains mysterious. Some researchers speculate they might be evolutionary remnants of a magnetic sense we once possessed but no longer consciously use. The study of biological magnetism has revealed just how pervasive magnetic sensitivity is in the natural world. From tiny bacteria to massive whales, from underground mole rats to high-flying birds, life on Earth has found countless ways to tap into the invisible magnetic field that surrounds our planet. This magnetic awareness connects creatures to their environments in ways that go far beyond simple navigation. Magnetic sensitivity helps animals time their migrations to coincide with favorable weather patterns and seasonal changes. It allows them to detect approaching storms by sensing the magnetic disturbances that often precede severe weather. It even helps some species coordinate their activities with the cycles of lunar and solar activity that create subtle but detectable changes in Earth's magnetic field. The implications of this biological magnetism extend beyond individual species. Entire ecosystems may be organized around magnetic patterns and cycles that we're only beginning to understand. The timing of migrations, the synchronization of breeding seasons, the coordination of activities across vast distances, all of these ecological rhythms might be influenced by the magnetic field that connects all life on Earth to the cosmos beyond. This creates a picture of our planet as not just a collection of separate species competing for resources, but as an interconnected web of life, all tuned to the same magnetic frequencies. Birds flying overhead, fish swimming in the depths, bacteria in the soil beneath your feet, all of them participating in a planetary conversation conducted in the language of magnetism. Yet this magnetic web of life faces new challenges in our modern world. Human technology creates artificial magnetic fields that can interfere with natural navigation systems. Power lines, radio transmitters, and electronic devices all contribute to a kind of magnetic pollution that some researchers worry might be disrupting the ancient guidance systems that life depends on. There are documented cases of whales and dolphins becoming disoriented near underwater cables carrying high electrical currents. Birds sometimes become confused during migration when flying near large radio installations. Even the magnetic fields generated by wind turbines have been suspected of affecting local wildlife, though the research on this is still ongoing. As our understanding of biological magnetism grows, we're also learning to appreciate just how remarkable these natural navigation systems are. The precision with which a bird can navigate across thousands of miles of featureless ocean, the accuracy with which a turtle can return to its birthplace after decades of wandering, the sensitivity that allows a bee to detect magnetic anomalies caused by buried metal, all of these abilities far exceed what our current technology can achieve. We've built global positioning systems that rely on satellites and atomic clocks, but a migrating songbird carries within its tiny body a navigation system that needs no external infrastructure, no power source beyond the food it eats, and no maintenance beyond what natural selection provides. It's a reminder that life has been solving navigation problems for millions of years longer than human civilization has existed. The study of biological magnetism also opens up fascinating questions about consciousness and perception. If some birds can actually see magnetic fields, what does that experience look like? How does a sea turtle's brain process magnetic information to create a sense of location and direction? What would it feel like to have a magnetic sense as acute as that of a migrating whale? These questions remind us that other creatures inhabit sensory worlds we can barely imagine. While we rely primarily on sight and sound to navigate our environment, the natural world is full of animals living in landscapes of magnetic sensation, electric fields, polarized light, and ultrasonic echoes. The magnetic field that we can only detect with instruments is, for many creatures, as vivid and immediate as the visual world is for us. This hidden sensory universe suggests that reality itself might be far richer and more complex than our human senses reveal. We think of Earth's magnetic field as an invisible force, but for countless species it's a visible, tangible part of their everyday experience. It guides their journeys, times their activities, and connects them to rhythms and cycles that span the entire planet. As you rest tonight, surrounded by creatures both seen and unseen who are navigating by Earth's magnetic field, perhaps you can imagine what it might feel like to possess such a sense, to feel the gentle pull of magnetic north, to sense the subtle variations that mark different locations on Earth's surface, to be connected through invisible threads to the spinning dynamo at our planet's heart. The magnetic field that protects us from cosmic radiation also serves as a navigation system for millions of species, a timing mechanism for ecological processes, and a communication network that connects life across vast distances. It's yet another layer of the remarkable story of our planet's invisible shield, a reminder that the forces protecting us also nurture and guide the incredible diversity of life that shares our world. So as your thoughts begin to drift towards sleep, remember that you're surrounded by a web of magnetic connections that link every living thing to the deep currents flowing in Earth's molten heart. The same field that deflects solar storms also guides the geese flying overhead. The same invisible force that creates aurora also helps flowers know when to bloom, and birds know when to migrate. Tonight, rest in the knowledge that you're part of this magnetic tapestry, connected through invisible threads to creatures great and small, all of us sharing the same protective embrace of Earth's ancient and faithful magnetic field, the field that asks nothing in return, but gives freely to all life the gift of direction, protection, and connection to the cosmic forces that shape our world. Tonight, let's venture into a realm where human ingenuity meets the invisible forces that surround us, where the same magnetic field that has guided migrating birds for millions of years now serves as the foundation for some of our most essential technologies. It's a story of how we've learned not just to detect Earth's magnetic embrace, but to harness it, study it, and depend upon it in ways that would have seemed magical to our ancestors. Picture yourself holding a smartphone in your hands. Inside that small device, no bigger than a deck of cards, lies a collection of sensors that would have amazed the greatest navigators of the past. There's a tiny magnetometer, smaller than a grain of rice, that can detect variations in Earth's magnetic field with precision that rivals the instruments used by professional geophysicists just a few decades ago. This miniature magnetic sensor is constantly taking readings, measuring the strength and direction of the magnetic field around you. When you open a map application and see that little arrow pointing in the direction you're facing, you're witnessing the result of countless magnetic measurements being processed in real time. Your phone has become a digital compass, reading the same magnetic field that guided ancient Chinese navigators and modern Arctic explorers. But the magnetometer in your phone is just the beginning of our technological relationship with Earth's magnetic field. High above your head, a constellation of satellites orbits our planet, each one equipped with sensitive magnetic instruments that monitor the constantly shifting patterns of our magnetosphere. These space-based observatories have names like Swarm, Themis, and the Van Allen probes, and they're providing us with an unprecedented view of how our magnetic shield responds to the ever-changing conditions in space. The data these satellites collect paints a picture of remarkable complexity. Earth's magnetic field isn't the static, unchanging force that early scientists once imagined. It's a living, breathing system that pulses and fluctuates with rhythms both rapid and slow. The field strength varies from moment to moment, as charged particles from the solar wind interact with our magnetosphere. It shifts over days and weeks as our planet's rotation carries different parts of the magnetic field into and out of the solar wind's direct influence. Ground-based magnetic observatories around the world add their voices to this global monitoring network. From the Arctic research stations of Greenland to the Antarctic bases scattered across the southern continent, from tropical islands in the Pacific to remote outposts in Siberia, sensitive magnetometers are constantly recording the subtle variations in our planet's magnetic embrace. These instruments are so sensitive, they can detect magnetic changes caused by underground mineral deposits, distant lightning strikes, and even the magnetic signatures of ocean currents as they flow through Earth's magnetic field. They form a kind of planetary nervous system, constantly feeling the pulse of magnetic forces, both near and far. The precision of modern magnetic measurements would astound the early pioneers of magnetic science. Where William Gilbert mapped Earth's magnetic field with compass needles and lodestones, today's instruments can detect changes in magnetic field strength that amount to less than 1 part in a billion. It's like being able to notice if a single grain of sand were added to a beach stretching for miles. This extraordinary sensitivity has revealed magnetic phenomena that were completely unknown to previous generations. Scientists have discovered that our magnetic field rings like a bell when struck by solar storms, vibrating at frequencies too low for human ears to hear but detectable by sensitive instruments. They've found that the magnetosphere breathes, expanding and contracting in rhythm, with changes in the solar wind like cosmic lungs drawing in and exhaling the charged particles that surround us. Perhaps most remarkably, they've learned that our magnetic field talks to itself. Magnetic waves generated by disturbances on one side of Earth can travel through the magnetosphere and affect conditions on the opposite side of the planet. It's as if our magnetic shield has its own internal communication system, coordinating its response to cosmic threats across thousands of miles of space. The study of these magnetic conversations has practical implications that extend far beyond scientific curiosity. Space weather, the term scientists use to describe the conditions in the magnetosphere, can have dramatic effects on the technology we depend on every day. When a particularly strong burst of charged particles from the sun interacts with our magnetic field, It can induce electrical currents in power lines, disrupt satellite communications, and interfere with GPS navigation systems. The Great Geomagnetic Storm of 1859, known as the Carrington Event, after the astronomer who observed the solar flare that caused it, was so powerful that telegraph lines sparked and caught fire, telegraph operators received electric shocks, and aurora were visible as far south as the Caribbean. If a similar storm occurred today, it could cause widespread blackouts, damage satellites, and disrupt the electronic systems that modern society depends on. To prevent such disruptions, scientists now monitor space weather as carefully as meteorologists track terrestrial storms. Networks of satellites and ground-based instruments provide early warning of approaching solar storms, giving power companies and satellite operators time to take protective measures. It's a remarkable example of how understanding Earth's magnetic field has become essential for protecting the technological civilization that field has helped make possible. The magnetic data collected by these monitoring networks has also revolutionized our understanding of Earth's interior. By studying how seismic waves from earthquakes affect magnetic readings, scientists can map the flow patterns in our planet's liquid outer core with increasing precision. They're learning that the geodynamo responsible for our magnetic field is far more complex and variable than anyone previously imagined. Computer models of the geodynamo now reveal that the currents in Earth's outer core organize themselves into intricate patterns that change over time, scales ranging from years to millennia. Sometimes these currents reinforce each other, strengthening the magnetic field. Other times they compete, creating the complex multipolar configurations that occur during magnetic reversals. These models have helped explain some of the mysteries that have puzzled scientists for decades. The South Atlantic Anomaly, that region where Earth's magnetic field is significantly weaker than elsewhere, appears to be caused by a patch of reverse magnetic flux deep within the outer core. This upwelling of oppositely directed magnetic field is gradually weakening the main field in that region, and some scientists believe it might be the beginning of a new magnetic reversal. The precision of modern magnetic monitoring has also revealed the influence of factors that previous generations never suspected. The gravitational pull of the moon and sun, the same forces that create ocean tides, also create subtle tides in the liquid outer core. These magnetic tides are incredibly small, but sensitive instruments can detect their regular rhythm as our planet moves through its orbital dance with its celestial neighbors. Even more remarkably, scientists have discovered that major earthquakes can affect Earth's magnetic field. When a massive earthquake shifts billions of tons of rock, it can create tiny but measurable changes in the magnetic field in the region around the fault. Some researchers are investigating whether magnetic measurements might someday help predict earthquakes by detecting the subtle magnetic changes that occur as stress builds up along fault lines. The magnetic monitoring networks that span our globe have also become tools for understanding climate and environmental change. Ocean currents generate weak magnetic signals as they flow through Earth's magnetic field, and changes in these signals can reveal alterations in ocean circulation patterns that might be related to climate change. The magnetic field generated by the jet stream high in our atmosphere can indicate changes in weather patterns and atmospheric dynamics. Lightning, those brief but powerful electrical discharges that illuminate storm clouds, creates electromagnetic pulses that can be detected by magnetic sensors thousands of miles away. By monitoring these magnetic signatures of lightning, scientists can track severe weather systems and study the global electrical circuit that connects thunderstorms around the world. But perhaps the most profound impact of our ability to measure Earth's magnetic field with such precision has been on our understanding of planetary magnetism itself. By comparing detailed measurements of Earth's field with magnetic data from other planets collected by space missions, scientists are beginning to understand what makes planetary magnetic fields possible and how they evolve over time. Mars, as we mentioned earlier, once had a magnetic field but lost it early in its planetary history. Magnetic measurements by orbiting spacecraft, have revealed that the Martian surface still retains the fossil magnetism of that ancient field, preserved in rocks that cooled and solidified when Mars was still magnetically active. These magnetic ghosts tell the story of a planet that once possessed the same kind of protective shield that still surrounds Earth. Venus, despite being similar to Earth in size and composition, has only a very weak magnetic field generated by its interaction with the solar wind, rather than by internal dynamo processes. Jupiter, on the other hand, has a magnetic field so powerful it could engulf the Sun if it were placed at the center of our solar system. These planetary comparisons help scientists understand the conditions necessary for generating and maintaining strong magnetic fields over geological time. The study of magnetic fields around other planets has also revealed phenomena that don't exist in Earth's magnetosphere. Io, one of Jupiter's moons, generates electrical currents as it orbits through Jupiter's powerful magnetic field, creating a cosmic electrical circuit that connects the moon to its giant parent planet. Saturn's magnetic field interacts with particles streaming off its rings, creating complex magnetic structures that change as the planet rotates. These discoveries from other worlds have enriched our appreciation for Earth's magnetic field and helped us understand just how remarkable our planetary protection system really is. The precise balance of conditions that allows Earth to maintain a strong, stable magnetic field over billions of years appears to be relatively rare in the universe, making our magnetic shield not just useful but precious. Modern magnetic research has also opened up entirely new fields of scientific investigation. Paleomagnetism, the study of ancient magnetic fields preserved in rocks, has become a powerful tool for understanding Earth's geological history. When volcanic rocks cool, they lock in the direction and strength of the magnetic field at that moment in time, creating a permanent record of past magnetic conditions. By studying these magnetic fossils, scientists have reconstructed the history of magnetic reversals going back millions of years. They've discovered that the frequency of reversals has varied dramatically over geological time, with some periods seeing frequent reversals and others remaining stable for millions of years. They've found evidence of brief magnetic excursions, periods when the magnetic field weakened and wandered, but didn't completely reverse. The magnetic record preserved in rocks has also become crucial for understanding plate tectonics, the slow movement of Earth's crustal plates that shapes our planet's surface. As new oceanic crust forms at mid-ocean ridges and spreads outward, it preserves alternating bands of normal and reversed magnetism that record the history of magnetic reversals. These magnetic stripes provide some of the strongest evidence for continental drift and help scientists reconstruct how Earth's continents have moved over geological time. Archaeological applications of magnetic measurements have revealed human history in ways that traditional archaeological methods cannot. Buried structures, ancient hearths, and even individual artifacts can create subtle magnetic anomalies that sensitive magnetometers can detect. Archaeologists now routinely use magnetic surveys to locate sites of interest before beginning excavations, saving time and preserving valuable historical information. The magnetic signatures left by human activities also tell stories about past civilizations. Ancient pottery kilns, metalworking sites, and even burned structures leave distinctive magnetic fingerprints in the soil. By mapping these magnetic traces, researchers can reconstruct the layout of ancient settlements and understand how past societies organized their activities. Medical applications of magnetic field measurements have opened up entirely new ways of studying the human body. Magnetoencephalography, or MEG, uses extremely sensitive magnetic sensors to detect the tiny magnetic fields generated by electrical activity in the brain. These measurements can reveal brain function with precision and time resolution that other imaging techniques cannot match, helping doctors diagnose neurological conditions and researchers understand how the mind works. The same magnetite crystals that help animals navigate may play roles in human biology that we're only beginning to understand. Some researchers have found correlations between variations in Earth's magnetic field and human health indicators, though the mechanisms behind these correlations remain mysterious. Others are investigating whether magnetic field changes might affect biological processes like sleep patterns, hormone levels, or immune system function. Industrial applications of magnetic monitoring have become essential for modern manufacturing and resource exploration. Magnetic surveys help locate underground mineral deposits, map geological structures, and monitor the integrity of pipelines and other infrastructure. Quality control in manufacturing often relies on magnetic measurements to detect flaws in metal products or ensure proper material composition. The magnetic sensors that began as simple compass needles have evolved into sophisticated instruments capable of measuring magnetic fields with extraordinary precision across a vast range of scales. From the massive magnetometers used in geological surveys to the tiny magnetic sensors in your smartphone, from satellite-based instruments monitoring space weather to laboratory devices studying magnetic materials at the atomic level, our ability to measure and understand magnetic phenomena continues to expand. As you rest tonight, surrounded by this invisible web of magnetic monitoring and measurement, perhaps you can appreciate how thoroughly we've learned to listen to Earth's magnetic voice. The same field that once seemed mysterious and unknowable to our ancestors has become a constant companion, monitored and measured and mapped with precision that reveals its every fluctuation and variation. Yet for all our sophisticated instruments and detailed measurements, Earth's magnetic field retains its capacity to surprise us. New discoveries continue to emerge from the vast databases of magnetic information that our monitoring networks collect. Unexpected correlations between magnetic variations and other natural phenomena continue to reveal new aspects of how our planet works as an integrated system. The magnetic field remains a frontier of scientific discovery, a realm where the invisible forces that shape our world continue to reveal new secrets to those patient enough to listen and sensitive enough to detect their whispers. It connects us not just to our planet's molten heart, but to the broader universe of magnetic phenomena that spans from the smallest scales of atomic structure to the largest scales of galactic magnetic fields. Tonight, as magnetic sensors around the world continue their patient vigil, recording every tremor and fluctuation in our planet's protective embrace, remember that you're part of a story that spans from ancient lodestones to modern magnetometers, from the first compass needles to the sophisticated instruments that now monitor our magnetic shield with unprecedented precision. The field that protects us also connects us, through the technology it enables and the understanding it provides, to a deeper appreciation of the invisible forces that make our world both habitable and knowable. Rest peacefully, knowing that our ancestors' simple compass needles have evolved into a global network of magnetic awareness that helps us understand and protect the precious magnetic shield that makes life on Earth possible. The story of how we predict and prepare for changes in our magnetic field reads like a tale of cosmic weather forecasting, where scientists peer into the future not by reading clouds and barometric pressure, but by monitoring the invisible dance between our planet and the sun. It's a field of study that has become as essential to our technological world as traditional meteorology is to farmers and sailors. Picture, if you will, a control room that looks like something from a science fiction film, filled with screens displaying colorful maps of magnetic field strength, charts showing solar wind velocity, and real-time data streaming in from satellites positioned throughout our solar system. This isn't fiction, it's the reality of modern space weather prediction, where teams of scientists work around the clock to forecast the conditions in Earth's magnetosphere days or even weeks in advance. The Sun, our normally reliable star, has moods that can dramatically affect our magnetic environment. Solar flares, those brilliant explosions on the Sun's surface, hurl charged particles into space at speeds that make jet aircraft seem stationary. Coronal mass ejections, massive bubbles of solar material weighing billions of tons, can travel the 93 million miles between Sun and Earth in as little as 15 hours when conditions are right. When these solar storms arrive at Earth, they don't simply bounce off our magnetic field like rain off an umbrella. Instead, they interact with our magnetosphere in complex ways that can strengthen or weaken our magnetic protection, create new current systems in the upper atmosphere, and sometimes overwhelm our defenses entirely. The result can be beautiful, in the form of aurora visible at unusually low latitudes, but it can also be disruptive to the technological systems we depend on. Space weather forecasters use a network of satellites positioned at strategic points around Earth and in space to provide early warning of these cosmic storms. The Advanced Composition Explorer, stationed 1.5 million kilometers sunward from Earth, serves as an early warning sentinel, detecting approaching solar storms and providing about an hour's notice before they reach our planet. Other spacecraft monitor conditions throughout the magnetosphere, watching for signs that our magnetic field is becoming unstable. The predictions these systems generate have become crucial for protecting everything from power grids to airline passengers. When forecasters predict a severe geomagnetic storm, power companies can take steps to protect their equipment by reducing power loads and disconnecting vulnerable transformers. Airlines reroute flights away from polar regions where radiation exposure increases during magnetic storms. Satellite operators put their spacecraft into safe mode to prevent damage from charged particles. But predicting space weather is far more challenging than forecasting terrestrial storms. While earthly weather systems are contained within our atmosphere and follow reasonably well understood patterns, space weather involves the complex interaction between solar activity, interplanetary magnetic fields, and Earth's magnetosphere across scales ranging from kilometers to astronomical units. The mathematical models used to predict space weather must account for plasma physics, magnetohydrodynamics, and the behavior of charged particles in magnetic fields, all while dealing with initial conditions that are often poorly known, and boundary conditions that extend far beyond our ability to measure directly. It's like trying to predict the weather while only having measurements from a few scattered weather stations and no understanding of what's happening beyond the horizon. Despite these challenges, space weather prediction has made remarkable progress in recent decades. Scientists can now forecast with reasonable accuracy when aurora will be visible at specific latitudes, when satellites might experience problems, and when power grids are at risk from geomagnetic storms. They've learned to recognize the magnetic signatures that indicate an approaching coronal mass ejection and can estimate its likely impact on Earth's magnetosphere. The models used for these predictions have revealed fascinating details about how our magnetic field responds to solar storms. During a major geomagnetic event, the entire magnetosphere can be compressed to half its normal size on the sunward side, while the magnetic tail on the night side can extend far beyond the Moon's orbit. Electric currents induced in the upper atmosphere can create their own magnetic fields strong enough to interfere with compass readings on the ground. These induced currents are more than just a navigation nuisance. When they flow through the conducting layers of Earth's atmosphere, they create electric fields that can induce powerful currents in any conducting structure on the surface. Power lines, pipelines, communication cables, and even railroad tracks can become conduits for these geomagnetically induced currents, which can damage equipment and disrupt operations. The 1989 Quebec blackout remains the most dramatic example of how space weather can affect earthly infrastructure. A coronal mass ejection from the sun created a geomagnetic storm so intense that it induced currents powerful enough to trip protective systems and shut down the entire Quebec power grid in less than 2 minutes. 6 million people lost power for up to 9 hours, and the aurora from that storm were visible as far south as Florida and Cuba. Since then, power companies have invested heavily in understanding and protecting against geomagnetic threats. They've installed monitoring equipment to detect the approach of dangerous space weather conditions and developed procedures for reducing system vulnerability during severe storms. Some have even redesigned their networks to be more resilient to the kinds of currents that space weather can induce. But power grids aren't the only technology at risk from space weather. The GPS satellites that provide positioning information for everything from smartphone maps to precision agriculture operate in regions of space where they're exposed to charged particles accelerated by geomagnetic storms. During severe space weather events, GPS signals can become unreliable or unavailable, affecting navigation systems around the world. Airlines have become particularly concerned about space weather because of its effects on both navigation and passenger safety. High-altitude flights, especially those crossing polar regions, expose crew and passengers to increased radiation during geomagnetic storms. The same magnetic field disturbances that create beautiful aurora can also disrupt radio communications between aircraft and ground control, forcing flights to lower altitudes where communication is more reliable but fuel consumption is higher. The increasing sophistication of space weather prediction has led to the development of specialized forecasting services for different industries. Power companies receive warnings tailored to their specific grid configurations and vulnerabilities. Satellite operators get predictions focused on the radiation environments their spacecraft will encounter. Airlines receive forecasts of radiation levels along specific flight routes, allowing them to make informed decisions about routing and altitude. Research into space weather prediction continues to reveal new aspects of how our magnetic field interacts with solar activity. Scientists have discovered that the effects of space weather aren't always immediate. Sometimes the magnetosphere stores energy from a solar storm and releases it hours or even days later, creating delayed effects that are difficult to predict. Other times, multiple small storms can combine to create impacts larger than any single event would produce. The study of historical space weather events has provided crucial insights into what might happen during extreme conditions. By examining records of past geomagnetic storms, scientists have identified events far more severe than anything experienced in the modern era. The Carrington Event of 1859, for example, was so intense that it would likely cause catastrophic damage to today's electronic infrastructure if it occurred now. Tree rings, ice cores, and other natural archives preserve records of past space weather that extend back thousands of years. These records show that while severe geomagnetic storms are rare, they're not unprecedented. Every few centuries, our planet experiences space weather events severe enough to significantly disrupt any technological civilization that might exist at the time. This historical perspective has led to increased efforts to prepare for extreme space weather events. Governments and international organizations have developed contingency plans for severe geomagnetic storms that could affect multiple technologies simultaneously. These plans recognize that in our interconnected world, the failure of one critical system can cascade into failures of others, potentially causing widespread disruption. The prediction of our magnetic field's long-term behavior presents even greater challenges than short-term space weather forecasting. While scientists can predict with reasonable confidence when aurora will appear or when a satellite might experience problems, forecasting whether Earth's magnetic field will reverse in the next 1,000 years remains largely beyond current capabilities. The complex interactions between the flowing iron in our planet's outer core, the heat sources that drive that flow, and the boundary conditions at the core-mantle interface create a system so complicated that even the most sophisticated computer models can only approximate its behavior. Scientists can identify trends and patterns in the magnetic field's evolution, but they cannot predict with certainty when the next reversal will occur or how long it will last. What they can do is monitor the current state of the magnetic field with unprecedented precision and watch for signs that might indicate an approaching reversal. The continued weakening of the field in some regions, the acceleration of magnetic pole movement, and the growth of anomalies like the South Atlantic Anomaly all provide clues about the magnetic field's current health and future prospects. Some researchers have suggested that we might be in the early stages of a magnetic reversal that could unfold over the next few thousand years. Others argue that the current changes are within the normal range of magnetic field variability and don't necessarily indicate an impending reversal. The debate continues, fueled by new data from monitoring networks and improved understanding of how magnetic reversals have occurred in the past. Regardless of whether a reversal is approaching, the study of our magnetic field's future has important implications for understanding how long Earth can maintain the protective shield that has sheltered life for billions of years. As our planet continues to cool and the radioactive elements that help power the geodynamo gradually decay, the magnetic field will eventually weaken and possibly disappear entirely, though this process will likely take billions of years. But long before that ultimate fate, changes in our magnetic field will continue to affect life on Earth in subtle but important ways. The strength and configuration of the magnetic field influences how cosmic rays interact with our atmosphere, affecting everything from climate patterns to the rates of genetic mutation that drive evolution. Understanding these connections requires a deep appreciation of how magnetic, atmospheric, and biological systems interact across a wide range of timescales. The prediction and monitoring of Earth's magnetic field has also become important for understanding our planet's place in the broader cosmic environment. As we discover more planets orbiting other stars, questions about their magnetic fields and their ability to maintain protective magnetospheres become crucial for assessing their potential to support life. The techniques developed for monitoring Earth's magnetic field are now being applied to study magnetic fields on other worlds. Spacecraft missions to Mars, Jupiter, Saturn, and other planets have revealed the diversity of magnetic environments that exist in our solar system and helped scientists understand the conditions necessary for generating and maintaining planetary magnetic fields. These comparative studies have reinforced just how fortunate Earth has been to maintain a strong magnetic field for so much of its history. The precise combination of size, composition, rotation rate, and thermal history that allows our planet to generate and sustain its magnetic field appears to be relatively rare, making our magnetic shield not just useful but precious. As you settle into rest tonight, perhaps you can appreciate the remarkable human achievement represented by our ability to monitor, understand, and predict the behavior of Earth's magnetic field. From the simple compass needles used by ancient navigators to the sophisticated satellite networks that now track every fluctuation in our magnetic environment, we've developed an intimate relationship with the invisible forces that protect our world. The scientists working in space weather centers around the globe are the modern equivalent of ancient watchers who studied the skies for signs of changing weather. But instead of looking for clouds and wind patterns, they monitor solar activity and magnetic field variations, using their understanding to protect the technological civilization that has grown up under Earth's magnetic protection. Their work reminds us that we live in a connected universe, where events on the Sun can affect power grids on Earth, where changes in our planet's molten core can influence the behavior of migrating animals, and where the same magnetic field that creates beautiful aurora also shields us from cosmic radiation that could harm life itself. Tonight, as you rest under the protective embrace of Earth's magnetic field, remember that this invisible shield continues its ancient work of deflecting cosmic storms and maintaining the delicate conditions that make our world habitable. Scientists around the globe continue their patient vigil, monitoring and predicting the behavior of this magnetic guardian, helping to ensure that the same field that has protected life for billions of years will continue to shelter us far into the future. The magnetic field asks nothing of us, expects nothing in return. It simply continues its faithful service, a gift from the physics of our planet that connects us to forces both terrestrial and cosmic. As our understanding of this invisible protector grows ever more sophisticated, so does our appreciation for the remarkable world we call home, and the countless invisible wonders that make life on Earth not just possible, but beautifully, mysteriously, perfectly protected. As we drift toward the gentle conclusion of our magnetic journey tonight, let's take one final, peaceful moment to appreciate the profound story we've explored together. We've wandered through the invisible realm that surrounds us, discovered the molten currents that flow thousands of miles beneath our feet, and marveled at the cosmic dance between our planet and the sun that creates some of nature's most breathtaking displays. Throughout this quiet exploration, one truth has emerged again and again. We live within an embrace so constant, so reliable, that most of us never pause to consider its presence. Earth's magnetic field is perhaps the most faithful companion our species has ever known, a silent guardian that has stood watch over our world for billions of years without asking for recognition, reward, or rest. Think about that for a moment as you settle deeper into comfort. Every breath you've taken tonight, every word you've heard, every peaceful thought that has drifted through your mind, all of it has been possible because of the invisible shield that wraps around our planet like the most gentle of embraces. The magnetic field that deflects cosmic storms, guides migrating creatures, and paints the polar skies with dancing light has been working tirelessly to maintain the delicate conditions that allow life to flourish. We've learned that this protective presence isn't just a simple force field, but a complex dynamic system that connects the spinning iron at our planet's heart to the charged particles streaming from the sun. We've discovered how this magnetic embrace has influenced the evolution of life itself, providing navigation systems for countless species and helping to preserve the atmosphere that makes our world so uniquely habitable. The story of Earth's magnetic field is also a story of human curiosity and ingenuity. From ancient navigators who first noticed the mysterious behavior of lodestones, to modern scientists who monitor space weather with networks of satellites, we've gradually learned to read the invisible language of magnetism that surrounds us. We've developed technologies that depend on this magnetic presence and created systems to protect ourselves from the occasional disruptions when cosmic storms overwhelm our planetary defenses. Yet perhaps the most remarkable aspect of this magnetic story is how it connects us to something far greater than ourselves. The same field that protects our small planet also links us to the vast cosmos beyond. When we see aurora dancing in polar skies, we're witnessing a conversation between Earth and Sun, a cosmic dialogue conducted in the languages of magnetism and light. The magnetic field lines that emerge from our planet's southern magnetic pole and curve gracefully through space before returning to the northern pole create invisible highways that charged particles follow across hundreds of thousands of miles of emptiness. These field lines connect the molten iron churning in our planet's core to the plasma winds that blow between the worlds, making Earth not just an isolated rock in space, but an active participant in the solar system's magnetic community. This connection extends backward through time, as well as outward through space. The magnetic field that surrounds you tonight is powered by the same primordial heat that was trapped within our planet during its violent birth 4.5 billion years ago. The radioactive decay of elements forged in ancient stellar furnaces continues to contribute energy to the geodynamo that generates our magnetic shield. In a very real sense, you are resting tonight within a protective embrace that connects you to the death of stars, the birth of planets, and the deep, slow rhythms of geological time. The magnetic field that keeps you safe links this moment to the entire history of our solar system and to the cosmic processes that created the elements in your body. As we've seen throughout our journey, this magnetic protection operates on every scale imaginable. At the smallest level, tiny magnetite crystals in living cells help creatures navigate across vast distances with precision that rivals our most sophisticated instruments. At the largest scale, our magnetosphere extends far beyond the moon, creating a bubble of magnetic influence that shapes the space environment throughout our cosmic neighborhood. The field strength varies from place to place and time to time, but its presence remains constant, whether it's deflecting a solar storm that could disrupt power grids, guiding a sea turtle back to its birthplace, or simply maintaining the atmospheric conditions that let you breathe easily as you listen to these words, our magnetic field continues its faithful service moment by moment, year by year, eon by eon. Modern science has revealed the incredible sophistication of this natural protection system. The magnetosphere doesn't just block harmful radiation like a simple shield. It actively manages the flow of charged particles, creating complex current systems, trapping dangerous particles in radiation belts far from Earth's surface, and channeling some particles toward the polar regions where they create those magnificent auroral displays. The magnetic field also serves as a kind of planetary memory, recording changes in solar activity, preserving evidence of ancient magnetic reversals, and maintaining connections between Earth's interior and the space environment that surrounds us. It's simultaneously a protector, a navigator, a communication system, and a historian, performing all these roles with an elegance that human technology can admire, but never quite replicate. Yet perhaps the most comforting aspect of Earth's magnetic field is its reliability. While it may wander and fluctuate over geological time, while it may occasionally reverse its polarity or develop temporary anomalies, it has maintained its essential protective function for billions of years. Through ice ages and warm periods, through mass extinctions and evolutionary explosions, through the rise and fall of countless species, our magnetic guardian has remained at its post. The same field that protected the first simple cells as they learned to harness sunlight continues to shield the complex technological civilization we've built today. The magnetic highways that guided the first migrating animals still carry their descendants across oceans and continents. The aurora that inspired the first humans to look up at the night sky with wonder continue to dance in polar darkness, painting temporary masterpieces across the canvas of night. This continuity across deep time reminds us that we are part of something much larger and more enduring than our brief individual lives. The magnetic field that protects us tonight has been standing guard since long before our species existed, and it will likely continue its faithful watch long after our current civilization has passed into geological history. As you prepare to drift off to sleep, surrounded by this ancient and faithful presence, perhaps you can feel a sense of connection not just to the planet beneath you, but to all the life that shares Earth's magnetic embrace. Every creature that has ever used our magnetic field for navigation, every generation that has marveled at auroral displays, every human who has ever been guided by a compass needle, all of us united by our dependence on the same invisible force. The magnetic field doesn't play favorites. It protects the smallest bacteria and the largest whales with equal faithfulness. It guides migrating butterflies and soaring eagles with the same invisible precision. It shields Arctic explorers and tropical islanders under the same magnetospheric umbrella. In the democracy of magnetic protection, all life is equal, all equally deserving of the field's constant care. Tonight, as magnetic observatories around the world continue their patient monitoring, as satellites in space track the ever-changing conditions in our magnetosphere, as the aurora possibly dance unseen in polar skies, remember that you are part of this vast, interconnected system of magnetic relationships. The same field lines that may be guiding charged particles toward auroral displays also extend through the space where you rest. The same geodynamo that powers navigation systems for migrating animals also generates the protective influence that surrounds your sleeping form. You are not separate from Earth's magnetic field. You are embraced by it, carried within it, protected by its ancient and ongoing presence. So let your breathing slow, let your thoughts settle like sediment in still water. Allow yourself to feel held not just by your bed or chair, but by the vast magnetic presence that extends from the molten iron at Earth's heart to the boundaries of our magnetosphere in space. Rest in the knowledge that the same force that has sheltered life for billions of years continues its faithful guardianship tonight. The magnetic field asks nothing in return for its protection. It expects no gratitude, requires no maintenance, demands no payment. It simply exists, a gift from the physics of our planet, a natural wonder that operates according to principles both elegant and mysterious. It reminds us that the universe is full of invisible forces working quietly to maintain the conditions that make life not just possible, but beautiful. As your consciousness begins to fade into the gentle realm of sleep, perhaps you can carry with you an appreciation for the remarkable world we inhabit. A world wrapped in invisible protection, guided by forces we can barely detect, sustained by processes that connect the smallest scales of atomic interaction to the grandest scales of planetary and cosmic dynamics. Earth's magnetic field is in many ways a perfect metaphor for the countless invisible forces that shape our existence. Just as we rarely think about the air we breathe until it's threatened, we seldom pause to consider the magnetic embrace that makes that very breathing possible. It operates in the background of our lives, as essential as gravity, yet far more mysterious, as ancient as the planet itself, yet as dynamic as tomorrow's weather. And perhaps that's exactly as it should be. The most profound gifts often come without fanfare, without demand for recognition. They simply exist, woven so seamlessly into the fabric of reality that we mistake them for granted certainties rather than the miraculous exceptions they truly are. As we conclude our gentle exploration tonight, consider how this invisible guardian reflects something deeper about the nature of protection itself. True safeguarding doesn't announce itself with sirens or fanfare. It doesn't demand acknowledgement or praise. It simply stands watch, quietly and faithfully, allowing life to unfold in all its messy, beautiful complexity. The magnetic field that surrounds you right now embodies this perfect form of care. It doesn't interfere with your daily choices or restrict your movements. It doesn't make demands on your time or attention. It simply maintains the conditions that allow you to make those choices, to move freely, to exist peacefully in a universe that can be both nurturing and harsh. This is perhaps why the story of Earth's magnetic field feels so deeply comforting. In a world where protection often comes with strings attached, where safety requires constant vigilance and effort, here is something that asks nothing of us while giving everything. It's a reminder that some of the most essential forms of care are also the most invisible, the most easily overlooked, the most quietly profound. Tonight, as you drift towards sleep within this magnetic cocoon, you join billions of other living beings who rest under the same invisible canopy. The whale navigating deep ocean currents, the bird settled in its nest after a long migration, the tiny bacteria in the soil beneath your home, all of us sharing this one planetary embrace, all of us equally protected, equally held. The magnetic field doesn't distinguish between species or continents, between day and night, between the powerful and the vulnerable. It simply enfolds all life in the same patient, enduring care. In doing so, it offers us a model of protection that transcends the boundaries we often create in our human understanding of safety and belonging. So as the night deepens around you and your thoughts begin to dissolve into the approaching realm of dreams, take with you this final, gentle understanding. You are held, right now, by forces both seen and unseen, by protection both ancient and eternal. The magnetic field that cradles our world tonight has been telling the same quiet story for billions of years, a story written in the language of invisible forces and patient care. It's a story that began long before the first eyes opened to see aurora dancing in polar skies, long before the first compass needle trembled toward magnetic north, long before anyone knew to give it a name or wonder at its purpose. And it's a story that will continue long after tonight's dreams have faded, long after the last satellites have fallen silent, long after our current understanding of magnetism has evolved into wisdom we can't yet imagine. The field will remain, faithful as always, carrying out its ancient duty with the same quiet dedication it has shown since Earth first learned to sing its magnetic song to the cosmos. In the end, Perhaps that's the most beautiful truth we can carry into sleep, that some things endure not because they seek recognition, but because they embody something essential about the nature of care itself. Earth's magnetic field stands as a testament to the possibility of protection without condition, of service without expectation, of love expressed through the simple act of creating space where life can flourish. So rest now, dear sleepy scientist, knowing that you are part of this ancient and ongoing story. Rest knowing that the same invisible threads that connect migrating birds to distant shores also connect you to the deep heart of our planet, to the dancing lights in polar skies, and to every living thing that has ever benefited from this most faithful of guardians. The magnetic field asks nothing more of you tonight than to simply exist, to breathe, to dream, to be held by its gentle and eternal embrace. And in that holding, in that quiet and constant protection, you are exactly where you belong, wrapped in forces both mysterious and magnificent, surrounded by the invisible love that keeps our small world safe in the vast and wondrous cosmos. Sweet dreams, and thank you for joining me on this journey through the invisible realm that surrounds us all. Until we meet again in another corner of scientific wonder, may you rest peacefully within Earth's magnetic embrace, held by the same ancient forces that have kept our world safe for eons and will continue their faithful watch long into the starlit future that awaits us all.